Great pleasure to introduce Anna Kerekes. She's a math student here in Cambridge, and she'll be talking about depth without the magic, inductive bias of natural gradient descent. Please, the floor is yours.
Thank you. So, as I just said, I'm Anna Kerekes, a third-year math student. I hope you can hear me well. Is it right? Okay. So, this summer I did a research project with one of my fellow third-year students from Hungary, Anna Mészáros, on deep learning, and I'm here today to talk about it.
Anna, if you feel more comfortable, you are allowed as a speaker to take your mask off.
Okay. I might do that because I have a pretty exciting voice. Okay. So, firstly, what was the motivation for our research? The first thing we started thinking about is that deep networks work surprisingly well, especially in the cases of rich models when our optimum is large class. And our ideas came to this case when the problem is really underdetermined and our network are over-parametrized. And we wanted to describe the optimum in these cases. So let's see an example of underdetermined problem. So one example is, for example, regression, when we have some points in a plane or in a bigger space, and we want to interpolate those points with a function. So more specifically, we have points x to x1 to xn, and we like to put a function on it such that we know the values in these points. So we know f(x1) to f(xn). And the question is, how can we find such a function? And if we look at the left, there is one example of that, just 5 points, and you see that the values are just 0, 1s. What kind of functions could we put on this, and how can we find a function which interpolates these points? And the first thing we must realize is that there are infinitely many such functions. Our model space is pretty rich. So we can see one on the left. That seems pretty basic. It's just a piecewise linear function. That's pretty simple. Then there is in the middle, still piecewise linear, but that seems less simple. And that one doesn't seem to generalize well. And in the right, we see a third one. That one is a smooth function. So we might want to find a smooth function. It's still pretty simple. So the thing we were thinking about is, okay, there are many, many different functions we can find by our algorithms or methods. One question is what kind of functions we like to find with our, and the other question is, how can we decide if we have a method, which function is found by it? So the question was, how can we define what kind of optimum did we find? So in the previous example, which function have we found? And to do that, it would be good to find the properties which have an effect on the optimum. One of the properties might be just how we initialize our method. The other things could be like, if you use gradient descent already has some regularization properties, so maybe that makes a difference. Or how we parametrize our problem, that might also make a difference. And in some cases, the stochasticity of our method can kind of imply which optimum we find. So let's see just some more examples of this when we have an underdetermined problem. So matrix completion, what's the problem here? Matrix completion is just a case when we have some entries of a matrix and we like to complete that matrix. In this case, we already see that if we have enough few entries, then there are a lot of matrices which have those entries. So here we see that this is a pretty underdetermined problem. Let's see a method where we find a matrix which completes our entries, and it has some special properties. I mean, the optimum has some special properties. So this method is called deep matrix factorization. How it works is that we have the beta matrix which we are looking for. We know some of its entries, and what we do is we parametrize it as a product of L matrices. L we call the depth of this method, and then run gradient descent on the matrices. So why is this interesting? Let's take a look at the diagram here. In this diagram, this describes the case when we only parameterize our beta as a product of two matrices, so W1 and W2. And what this diagram tries to explain is that if we move the middle entry of our matrix, so like this is the first picture on the left, you move the middle entry, the red one, then the entries what move will be in the W1, that row which is colored, and in W2 the column which is colored. So in the beta product, it will just be the cross. So if we move one entry, the whole cross will move together with it. Why is this interesting? This is interesting because with the gradient descent, every time we move a single entry, whole cross will move with it. And as we increase the depth, it won't be a cross anymore. It will more like it will be a smoother motion. So the things which are close to each other will move together. And that will give our method a really interesting property, which is that the solution, the optimum this method finds, will be a low rank matrix. And as we increase the depth, it will kind of be even lower rank. So this won't just find any optimum, it will find the low rank optimum. So let's see another example. Same problem, matrix completion, but now we just parameterize it directly. So it's the L equals 1 case. What we find here is that cross thing or the smoothness kind of disappears. And when we move a single entry, just a single entry will move. And in this case, the thing what will happen is that the observed entries will be moved by the gradient descent to the right entries, and the unobserved entries just stay at initialization. So in this case, we also find a kind of optimum, but it's not that interesting. It just will be an obvious one. So let's look at another example just to get a better feel of this. In this case, we thought about separating separable classification. The problem is that we have some dots and dots in our space, and they each have a label +-1. And we like to separate them with a hyperplane, so the +1s are on one side and the -1 on the other. Why is this connected to the previous things we did? It's connected because it's also an underdetermined problem. In the case when they are separable, in our tool, the data set will always be separable. And if we look at this, we see it's separable, and we also see that there are many lines which might separate this data set. So that's why it's an underdetermined problem. So how can we tackle this problem? One example is gradient descent with direct parameterization. The interesting thing about this is if our separator is just beta, and if we run gradient descent on it, what we find is that the length of beta just goes to infinity. So that's not too interesting, but the angle can be something to consider. If we consider where the angle converges, so the angle of the separator, we find it will be the solution of the L2 large merging problem. So that's something we already know, and we see on the picture a case of that. The striped lines just show the margin, and the black line is our separator. And another example is a different parameterization. Same problem, separable classification and gradient descent. The only thing changed is the parameterization. So now it's not just a direct parameterization, but instead we take a pointwise product of L different vectors as our separator. The length of the separator still goes to infinity, but the angle will converge to a different direction. Our direction is now will be another LP regularization, but now P is, if L is at least 2, then P will be 1 or smaller, which means we get a sparse solution. Here on the diagram, we see an example where we are in 2D and we got one of the x's, which is exactly a sparse solution. Yeah, so what we got, let's just stop for a second. What did we get so far? So we started from thinking about underdetermined problems. Underdetermined problems with different solving methods. And in matrix completion, we ran gradient descent, but with 2 different parameterizations. When we ran on deep matrix, when we ran it on matrix factorization, so we took matrices, multiplied them together and ran gradient descent on that, we found that the solution will be a low rank solution. But when we did it with direct parameterization, nothing really happened except we found the observed entries, but everything else stayed at initialization. So that's the matrix completion. And in separable classification, same thing, we run gradient descent. But on the direct parameterization case, we found an L2 large margin solution. And in diagonal parameterization, we found an LP large margin solution, sparse solution, where P is like smaller than 1. So what you see here is parameterization can have a huge effect on the optimal we find. That's already great, but what if we eliminated parameterization? What would we find them? So our next idea was that, okay, it seems like parameterization has a huge effect, but what if we try to eliminate it somehow? And what we can see on this figure is 2 parameter spaces with those the small pretty dark blue circle being the optimum. And we see 2 different trajectories, the yellow and the red in the 2 spaces, and they both end up in the optimum. And what we see then in the hypothesis space, they find a different optimum. So that's what we saw so far. Different parameterizations might end up in different optimums. And now our idea is to instead of run gradient descent on the parameter spaces, we might try to run it in the hypothesis space. So we just try to eliminate this whole parameter dependence. And to do that, we need a distance on this hypothesis space. Usually it's the KL divergence. And this KL divergence is described by the Fisher information matrix. So let's see this a bit more in detail. This method is called natural gradient descent. And what it does is that it describes the probability distribution of the label or output with the knowledge of X, the input, and a parameter. And this will be just a gradient descent on this probability statistical model space, and with the distance KL divergence. And the form is the same as for gradient descent, just we get this F-1 in it, which is the Fisher information matrix. And the gradient flow is also, natural gradient flow is the same as the gradient flow, just with the Fisher information matrix. And the good thing about this is that it's parameterization invariant. So if we look at our picture again, if we look at the dotted lines, those are the natural gradient descent trajectories. And in the hypothesis space, they map to the same thing, which just means they are that this method is parameterization invariant. So let's see what happens if we try to use, let's see one more, bit more detailed example. So we talked about separable classification, but as just a reminder, we had some data points x1 to xn, which had labels plus minus 1. Those are y1 to yn, and our separator was beta. And now we have to describe the probabilities of y being 1 or minus 1 to be able to use natural gradient descent. This is a common choice of probabilities. And for this, the loss function, which can be found by calculating the negative log likelihood, will be just the logistic loss, which is a widely used loss function. And all the other calculations are just the calculation of the gradient of the loss, which we need for natural gradient descent, and the calculation of the Fisher information matrix. One thing to keep in mind here. Yeah, one thing to keep in mind here is that in the last bottom line, we see that the Fisher information matrix can be get by getting the expected value of the Fisher information matrix for each data point. And we never said we know the distribution of the data points. So in our experiments, we just use uniform distribution. But if we have some prior knowledge of the data points, we might use a different Fisher information matrix. Yeah, but we just use the uniform distribution. And now let's just take a step back again. What did we see so far? So at the first part, we saw that parameterization plays a pretty important role in what optimum we get with Euclidean gradient descent, which is just the general gradient descent. But now we found a method which is called natural gradient descent, which eliminates this effect. And our question could be, is this invariance good, or does this hurt generalization? Because you saw that gradient descent with some specific parameterization had pretty nice generalization properties, like finding lowering solutions or finding LP regularization solution. So now the question is, what about natural gradient descent? What kind of solutions can it find? And does this invariance hurt the generalization? And now we just try to understand natural gradient descent on the problem you've seen before, first on matrix completion. So let's look at this diagram for a bit. The first thing to see is that the y-axis is just the depth of the matrix factorization. So we see L equals 1 in the first row, L equals 2 in the second, L equals 3 in the third, and L equals 5 in the fourth row. And the x-axis is just Euclidean gradient from the left to the right, Euclidean gradient flow, Euclidean gradient descent, natural gradient flow, and natural gradient descent. And what we already see the left part, because we see for L equals 1, if we move the middle, only the middle will move. So everything else stays fixed. But if we have L equals, at least L equals 2, we have the cross. L equals 3 is something like the cross, but with a bit more colors, and L equals 5 has even more colors. We see that stuff like move together, but for natural gradient flow, it seems like nothing really moves, which for natural gradient flow, we saw that it's parameterization invariant. So we kind of expect this to happen. We expect it to be, for any parameterization, to be the same as the direct parameterization. So it's not surprising that if we move the middle, only that will move. And for natural gradient descent, so here the invariance property shouldn't necessarily hold. It only holds for natural gradient flow, but with small enough step size, we would expect this to happen. In some of our experiments, we saw some colors, but mostly the invariance. So just as a summary, what we see now that natural gradient descent behaves as the direct parameterization in the matrix completion case. So only the observed entries are taken to their position, and the unobserved entries do not move and just stay fixed. So yeah, here we lose the generalization. Some more experiments on this. So still matrix completion, and we try to complete a matrix which is low rank. It has rank 5. And the pictures, what we can see on the left, we have a diagram where one axis is the test loss, and the other axis is the number of observations. And what we see is that the blue line on the top, the Euclidean gradient descent with direct parameterization, nothing really happens. With natural gradient descent, the same. We see that they move together, which is kind of what we expect. And with Euclidean gradient descent with at least L equals 2, so where the factorization effect comes into place, we see that the test loss drops. Also for the other diagram, what we see on the two axes, one of them, the y-axis, is the effective rank at convergence, and the x-axis is the number of observations. So here again, what you see that for Euclidean gradient descent with direct parameterization, which is the blue line on top, the effective rank doesn't change. That's kind of what we expect. Same for natural gradient descent, and they moved nicely together, which kind of confirms that they do the same thing. And with when the factorization actually comes into place, which is like the orange line and the green line, then we see a drop in the effective rank, which confirms our results from before. So now let's look at separable classification with the same thing. So far, we found that in separable classification, when we run gradient descent, Euclidean gradient descent with direct parameterization, then that's the left picture, the picture A. Then we get an L2 large margin solution. And when we run it with a diagonal network, so with the pointwise product of L different vectors, then what we get is a sparse solution. That's picture B. These are things we already see. Now, the other two pictures come from natural gradient descent. And what we did is we use the same parameterizations as before, so direct parameterization and diagonal parameterization. And what we can see first is that they give the same thing. That's good because it should be parameterization invariant. The other thing we can see is that it doesn't look like a sparse solution. And it's also not the same as A, the L2 regularization. So now the question could be, it's not a sparse solution, it's not an L2 large margin problem, what is it then? And is it even a norm as before? Because all what we got so far were norms, so maybe it's a norm as well. Okay, so we see that if it's a norm, what we found is an invariance property of this method. And what it means is that if we transform our data set by a matrix A, then the trajectory will also transform by A transpose. So more specifically, if we have X, which is our data set for separable classification with full rank, and we have an A invertible matrix, then the trajectory with natural gradient descent beta t will be A transpose beta prime t, where beta prime was just the trajectory for the transformed data set. So the trajectory just changes by A transpose. This only holds for n greater than d, where n is the number of data sets, d is the dimension. But for the other case, when the problem is over-parameterized, then this holds in the span of our data set. So it's almost the same thing. And what this means here is from this, you can get, it can't be an LP large margin solution, because if we take our matrix A to be just scaling of one coordinate, then here we see how it transforms our trajectory, but that transformation doesn't hold for the norm solutions. So this can't be an LP large margin solution. So now we try to classify it somehow differently, because this did not work. So our next classification idea was ordinary least square solutions. And the motivation for that was that an ordinary least square solution has this invariance property, which is described with the A transpose. So if we have so the ordinary least square solution, it shows that if we have points x1, x2, xn, and there are corresponding variables y1, y2, yn, then we just want to minimize this y minus x beta with choosing beta. And the thing to remember here is that this is a regression, not a classification. So usually their solutions does not agree. But it has the invariance property. So it might be our solution for the natural gradient flow case. And we found that it's actually true. So for the case when b is greater than n, so our problem is over-parametrized, we found this pretty nice theorem, which says that if x is full rank, then the logits x beta are asymptotically linear in T with direction vector y, which means that if a point has label +1, then this logit will converge to 1, and if label has -1, it will converge to +d and -d. So if we look at this picture, it kind of confirms it. This is an experiment we ran where we can see that the positive data points will just converge to the +1, and the negative data points converge to the -1 as t goes infinity. So it kind of confirms this theorem. And this is exactly the ordinary least square solution. So what we wanted to see. And another comment about this is that we found that the natural gradient descent converged to this OLS faster than the Euclidean gradient descent converged to the L2 large margin solution, which is interesting. And even more interesting is that this result with the OLS solution also holds for nonlinear systems. So far we used linear networks for our experiments, but this result would also hold for non-linear networks. The result is exactly the same. We have classification where beta is our separator, and we have logits depending on the data X and beta. And assuming that the system is over-parametrized and the Jacobian of the system is full rank, then these logits will converge to these logits will grow asymptotically linearly with direction vector 1. So this is, and let's look at some more experiments. So this is separable classification still, and our experiment was on sparse classification. So our point had 1,000 dimensions, but only 20 non-zero components. And this picture kind of describes what we found. The y-axis is the test accuracy, and the x-axis is the number of observations. And the gray area is where our theorem holds. So that's kind of where we classify the solution already. And there are quite a few lines, so let's just go through them. The first line we see is the Euclidean gradient descent with L equals 1. That's the blue line. And we see 3 other Euclidean gradient descents with L equals 2, 3, and 4. Those are the orange, green, and red lines. When we see that they all perform better than the Euclidean gradient descent with L equals 1. Seems like that the red might perform worse than the other two, but actually probably after some more time, it would also work just as well, because it takes more time to converge if we increase the L number. And there is one more line, which is the natural gradient descent. And as kind of expected, it doesn't perform as well as the Euclidean gradient descent on this sparse problem. Yeah, so we see here that it just doesn't perform as well. So let's just like summarize our results so far. So when we started this, we were thinking about the importance of parameterization. In Euclidean gradient descent, we found that parameterization has a large effect on the solution or the optimum found by our method. And in matrix completion, we found that direct parameterization just doesn't give any interesting results. And matrix factorization gives low-rank solutions. Similarly, in separable classification, direct parameterization and diagonal networks gave different solutions. But then we found this method, natural gradient descent, which is parameterization invariant. And this method did not perform well on the experiments we did, but it converged pretty fast on the OLS solution. So it didn't generalize well on the experiments made up by ourselves, but it might perform pretty well on other experiments. So if we'd like to answer the question, does invariance hurt generalization? The answer is it does sometimes, like in matrix completion, it does, but it might not hurt it in other cases. And we also see that it can be still pretty fast, the natural gradient descent. Some more comments about this is the same picture as we saw before, but there is one more line on it, which is the striped line. The striped line is just another natural gradient descent. And more specifically, it's natural gradient descent on population, which means that as we calculated the Fisher information matrix, we calculated in our experiments on data points, on our data points. But we could calculate it on a bigger data set. That's what happens here. And we see it kind of enhances the performance, but it doesn't make it any better, doesn't make it better than Euclidean gradient descent. So that's just something to comment about this. And there is another thing we could keep in mind is something we didn't think a lot about, but we mentioned it at the beginning, is that initialization can play a role in the optimum we find in some specific cases. For example, when we do matrix factorization, we already initialize from a Gaussian, which can be pretty low rank if we multiply a lot of Gaussian. So it came out if it's already low rank, that's why we find the low rank solutions. But our experiments kind of showed that it doesn't seem to be the case. So maybe in some other cases, initialization plays a bigger role, but we found that here it seems to be just a small thing. Yeah. And I think that's it. I went a bit too fast, but thank you. And is there any questions? Are there any questions?
Thanks for a very interesting talk. Any questions? So that I have some. So that's very fascinating with the matrix completion. So you showed the graph with the when you do the sparse classification. But I would assume you would have exactly the same behavior or similar behavior for matrix completion. This must depend on the number of samples, right?
Yeah.
Yes. How did that look? Did you see any difference there?
Is it this?
So this one here is the number of observations. Oh, right, exactly. So how do we, so the part that I'm trying to understand is now when we do the recovery. So because I come from a compressed sensing or matrix completion background. And in that case, when we are doing the standard convex optimization problem, the key is when that will actually match the low rank or the minimum rank solution. So what we do here is that when you compute the actual rank, what do you actually do? Do you compute the number of smallest singular values and then sum them up? Or sorry, and take the number, so the rank is now the number of the singular values that are above some threshold.
I think in the effective rank, which is needed all singular values, there was so I think in the effective rank we took kind of a mean of the singular values, which I think.
Because so the reason why I'm asking this is that because the rank is a completely discontinuous function, so numerically it doesn't make any sense to compute it.
Yeah.
So the old matrix completion theory is about saying when the nuclear optimization matches the actual low rank solution, which is the true low rank, but that doesn't make any sense numerically. So what I'm trying to understand here is that what we're actually computing is something which isn't an actual low rank. It is an approximation to it.
Yeah.
And that's what I'm trying to understand, because this is something you cited Aurora's paper. When I read that paper, I could never understand exactly, what are we saying? Because the term rank doesn't numerically say anything, and it wasn't clear, what are we actually computing?
Yeah.
Did that make sense?
Yeah.
Yes.
Yeah, it does. If I remember right, what we did is calculated this effective rank approximation, which should somehow approximate the rank.
But is that the standard? So like in MATLAB, when you write rank, is that the command?
In MATLAB, I have no idea.
Oh, I see, because you're writing. Yeah. You have to forgive me. I'm so old. I'm still using that.
I can jump in.
Yes,
to answer. This is so somebody came up with this approximation. It's a differential approximation of rank, and it's you take the absolute singular values, so
Yes.
absolute singular values, normalize them, pretend that they are a probability distribution, so divide by the sum, and then you calculate the Shannon entropy.
So that's a completely different thing than the standard numerical linear algebra computation.
It will, if the thing is low rank, if
Yes.
the matrix is low rank, it's going to correspond to the effective rank, but it also gives like an approximation to the like kind of something similar to a rank for a full rank matrix.
But I think that's the part that I don't understand, because I can take a matrix which has super low rank, it's zero matrix, and I add a perturbation of 10 to the minus 80, and it will have full rank. But numerically, that doesn't make any sense, because the perturbation that I see is so tiny that it will be smaller than the distance
Yeah,
of any
so
point.
I would think that in that case, this effective rank would actually also be very small.
Yes, but what I'm at, so the statement about the low rank depends on how you compute the rank. So if MATLAB does something and this does something else, the question is, what do we mean by low rank?
I guess close to a low rank matrix.
No, yes, so we have different ways of saying. So that's why I'm curious about the computation. This is great work, by the way. I'm just curious about the actual the way that we compute it. All right, other questions? Well, oh, please, yes.
I mean, just so also super interesting part as well. Do you have some conceptual understanding of why this invariance, why this invariance plays together with the generalization as it does?
So the idea was, or at least in my head, the idea was that if this parameterization has like such a nice generalization properties, one of the parameterization, like such a nice generalization properties, but then the other one doesn't have any nice generalization, then if something is invariant, I don't know, that seems to be somehow contradicting, like.
Yeah, this.
Sorry?
Yeah, so this is basically what I'm asking. Why is the invariance part of generalization? So you've shown that it does, and this is super interesting.
Yeah, I think I've only shown that it sometimes does. So in my head, it doesn't mean that it never can have like nice generalization properties. In my head, it just means that now we found some cases where this doesn't seem to have any nice generalization properties. But honestly, I would be interested if there are cases and it's like really nice.
I'm also asking because we have been interested, actually quite a lot of people here in the room have been interested to use neural networks for solving inverse problems. And there are also lots of the discussions are going in this direction that there seems to be this trade-off between performance generalization and actual mathematical guarantees, which then, mathematical guarantees turn into putting constraints onto the network to get these guarantees. And yeah, so I don't know if it's just a matter in this case of just constraining the network being more constrained and having less freedom because it means over this invariance property or something more. Yeah.
Can I say something? I mean, I have no idea. I might be completely wrong. But I think it really resonates with this idea that you're just doing some sort of implicit regularization. So it feels like natural descent might converge quicker to, to a solution that.
And hence it doesn't.
Yeah, exactly. But it's like you just go through like quickest path instead of going to a path that's kind of regularized. So I think that it is actually quite interesting when you're showing the plots where you have like kind of the optimal space and like they're converging in different places. I guess the problem is not very imposed, so all the solutions are pretty much okay, then just use natural gradient because it probably converge faster.
Okay, but then what you're saying is it's more of a preconditioning effect of natural gradient descent rather than.
Well, I think it's more a preconditioning effect of the parameterization. So it's, I understand it's kind of the opposite. So I think that if you think that your problem is imposed, you could either use a parameterization that already takes you through a nice route where your solutions will be probably more suitable to be good solutions for your problem. Or you could maybe just add regularization to the objective function and then do natural gradient descent and get rid of this second layer of implicit regularization.
I think if I can add the machine learning angle here, I think the broader observation that this fits into is that often optimization algorithms that are more efficient at finding an optimum in deep learning are worse at generalization. So there tends to be a trade-off between how quickly you converge to a solution and how good a solution you converge to when there are multiple optima that have different generalization properties. So you can kind of say that NGD or natural gradient descent is very greedy. It's just going to fit the data very quickly and very efficiently. And it kind of forgets about generalizing elsewhere. That's sort of a very, very hand-wavy.
So doing a very good job in optimizing.
Yes, in some sense it seems. So like it solves the matrix completion problem very lazily by only moving the entries which are observed.
By the way, just a comment, Anna, the only reason why I don't have any student participants is because apparently I think we're using this wrong student link. And I just saw some Slack messages. We're saying, yeah. So I have no idea.
Because they used the one I think on that's broadcasted on the bulletin, right? But that doesn't work. And we know
apparently they're not using the one.
Actually, we're in a different
Anyway, it's being recorded, so they can watch it. But I'm just saying this is the only reason.
Well, okay. Well, there's been a couple of hiccups, but that's yeah. Other questions? Well, I'm very happy that we had such a lively debate afterwards, reflecting a very interesting talk indeed. So let's